Hello students, welcome back to Learn24. In this video, we are going to cover our last colligative property called osmotic pressure. Before going to the osmotic pressure, let me explain what is osmosis. Osmosis is nothing but the flow of solvent particles through a semi-permeable membrane from lower concentration of solution to the higher concentration of solution. That is, flow of solvent particles through a semi-permeable membrane from the lower concentration of solution to the higher concentration of solution. The solvent particles will move from here to here through a semi-permeable membrane, or the solvent particles will move from pure solvent side to the solution side through a semi-permeable membrane from pure solvent to the solution side. And you know what? This semi-permeable membrane will only allow the passage of solvent particles, not the passage of solute. They only pass the solvent molecules. Now, you have a clear view about the osmosis, right? Now, let me explain about the osmotic pressure now. As I told you, the solvent particles will move from pure solvent side to the solution side through this semi-permeable membrane. Now, I have to stop this flow of solvent particles. I have to stop the osmosis. For that, I have to apply some pressure. And now, can you tell me where should I apply the pressure to stop this flow of solvent? Can you tell me that? Yes, I have to apply pressure on this side, on solution side. I have to apply a pressure to stop this flow of solvent particles. That pressure is called osmotic pressure. Osmotic pressure is the pressure that stops the flow of solvent, or it prevents the osmosis. It prevents the osmosis. Now I can represent this osmotic pressure as pi. Pi is the osmotic pressure, and this pi is directly proportional to C and T. Pi is directly proportional to C and T. C is the molarity and T is the temperature. So the osmotic pressure is directly proportional to molarity and temperature. In order to remove this proportionality sign, I have added a constant called R. You all are familiar with this constant, right? It's a gas constant. R is a gas constant. That pi is equal to RCT. Now we have to find out the molar mass of solute, right? Yes. As we know, C is N2 divided by V. C is equal to N2 divided by V. I just substituted this in this equation. Pi is equal to RCT. Now, pi is equal to R into N2 divided by V into T. Now, I removed V from here and placed in the left hand side. Now I got the equation pi V is equal to R N2 T. Pi V is equal to R N2 T. N2 is the given mass divided by molar mass. N2 is equal to W2 divided by M2. I just substituted this here. Then I got an equation pi V is equal to W2 divided by M2 into RT. M2 is what I have to find out. M2 is equal to W2 into RT divided by pi V. And I got an equation to find out the molar mass of solute. M2 is equal to W2 RT divided by pi V. By knowing these terms, I can find out the molar mass of solute. Again, it's a colligative property. Depends only on the number of solute particle, not on the nature. So the osmotic pressure is a colligative property. Now, let me explain about the reverse osmosis. It's just reverse to the osmosis. What was osmosis? Flow of solvent particle from pure solvent to the solution side through a semi-permeable membrane. Now, In order to stop this osmosis, I have applied a pressure here called osmotic pressure. Now, when I apply some more pressure which is greater than this osmotic pressure, then this solvent will move from solution side to the pure solvent side. The solvent particles will move from solution side to the pure solvent side when the applied pressure is greater than osmotic pressure. Direction of osmosis is just reversed. Direction of osmosis is just reversed by applying some pressure which is greater than the osmotic pressure. It's called the reverse osmosis. We can find out a big application with this reverse osmosis, that is separation of salt from the seawater. I will tell you how. Now I have a salt water here, that is a solution. Salt water here and a pure solvent, let it be the water. Now I have the salt water and pure water here. Now when I apply some pressure which is greater than the osmotic pressure, the water molecules from this side will move to the pure solvent side, which will result in the deposition of salt particle in the bottom of this side, right? This is how I can separate the salt from seawater. It's a big application of reverse osmosis. Coming to the last topic of our chapter called abnormal molar mass. We found out some molar masses using the colligative properties, right? That molar masses will not be equal to the normal or expected values. That is, value of molar masses calculated by using colligative properties will not be equal to expected or normal value. Either it will be lower or higher. It's called the abnormal molar mass. In order to rectify this, Van Hoff introduced a factor called Van Hoff factor I. In order to rectify this, Van Hoff introduced a factor called Van Hoff factor. And Van Hoff factor is equal to normal molar mass divided by abnormal molar mass, or observed colligative property divided by calculated colligative property. This is what Van Hoff factor is. Now let me show you how this factor modified these four equations. First colligative property was relative lowering of vapor pressure, and the equation for relative lowering vapor pressure was Pi naught minus Pi all divided by Pi naught minus N2 divided by Ni was the equation for relative lowering of vapor pressure. But now Van Hoff modified this equation by placing I here, and this is the modified equation for the Van Hoff factor. For the relative lowering of vapor pressure, Pi naught minus Pi divided by Pi naught is equal to I into N2 divided by N1. Now, second colligative property was the elevation of boiling point. Equation was delta Tb is equal to Kb into m. What is Kb? It was ebullioscopic constant, obviously. Delta Tb is equal to I into Kb m. This is the modified equation for elevation of boiling point. Third colligative property was the depression of freezing point, and the equation was delta Tf is equal to Kf into m. Kf was the cryoscopic constant. Now the equation modified as delta Tf is equal to I into Kf into m. This is the modified equation for depression of freezing point. And the last colligative property, osmotic pressure. Pi is equal to I into N2 divided by V. RT is the modified equation for osmotic pressure. This is the abnormal molar mass and Van Hoff factor. By this, we are ending our chapter called Solutions. It's a very easy chapter when compared to all other chapters. So you must score all the marks while during the examination. So all the very best, and if you have any doubts regarding these topics, just comment it. I will answer them. See you in the next video. Bye bye.